Hi, welcome to our webinar. My name is David Morganson. I'm a manufacturing applications engineer here at CCAT. CCAT is Connecticut Center for Advanced Technology. So we're a not-for-profit and we're here to serve you, our customer, and thanks for joining our webinar. So our agenda, just a quick welcome. Thanks for joining us. I'll give you a quick overview of what CCAT is and some of the things we do. And then we've got an excellent presentation from Alex here, has NC Software Solutions. And it's a pretty innovative solution. It's something that maybe some people weren't expecting could be automated or could be done. And it's been done. It's really useful for rework or forgings or a number of other things I'm sure you can come up with. So looking forward to that. So a little bit more about CCAT. I'll tell you about our vision. Transformative solutions for a connected world. So that actually means something. The vision means something. So right now there are many useful pieces of technology, but the race is to connect them better, right? So the data is there, it's easy to catch, the sensors are cheap, the storage is practically free for the data, but it's really how you connect it and how you connect it across various parts of the supply chain and the manufacturing chain. So our mission is to lead the advancement of applied technologies, power the workforce of the future, and inspire change. So we hope that you learned something from this and it's something that you find useful. So we're an applied technology demonstration and training center. We validate things that we look at, we demonstrate them, and we assist with the adoption of the leading edge technologies, mostly in Connecticut, but also in the nation's advanced manufacturing supply chain. So we can also help with some training and upskilling. Great example, we've got some model-based definition training we just ran through recently, Origin Checkmate, we've run Vericut, and we've got this here for you today. I'm sure if you want to get the product and do some training, we could figure out a way to host it. So we're kind of split into three main areas at CCAT. The advanced design, automation, metrology section is primarily where I work out of. We also have advanced technologies, optimization, and machining. So that's where things are actually made. And then the Advanced Composites Technology Center, that's another example of a technology that used to be highly artisan, and it still largely is. So you have to hand lay, and there's quite a bit of science, engineering, and artist technique on how to create an excellent composite and get the results that you need out of the composite. So CCAT's working with Pratt & Whitney to figure out ways to automate that to get repeatable results using automation. So advanced design drives advanced manufacturing, and then you need advanced metrology to inspect the resultant parts. So it all ties in. So model-based definition, usually what was done is you think of a part in your mind, and then you reduce it to orthographic views, top, right side, and so forth, maybe some section views, and then you dimension it out. Now we've got the ability to solid model things, SolidWorks, NX, CATIA, you name it. Everybody's got three-dimensional modeling now. And then still we have that step where you take that solid model and you reduce it to views. And nothing necessarily wrong with that, but now you have two sources of truth. You've got your solid model and your print. And yes, they tie together, but as the prints and parts get more complex, that becomes more careful reading. You really have to be very tedious in how you read that. And also you have to enter the data multiple times when you want to manufacture, inspect it. So that's not true of the model-based definition. So we've got a few webinars on that. We're really looking to drive that. Generative design, instead of designing the part and doing the finite element analysis, you let the finite element analysis design the part. Industrial Internet of Things, so that we're touching a little bit on that here today. An example is you can put a sensor in a machine and figure out exactly where your part is before you machine it, instead of kind of creeping up on it with some offsets or what have you. We've got an X-ray scanner here at CCAT. We can do a three-dimensional X-ray scan of a part, see what's going on inside of it, non-destructive. Automation, robotics, directed energy deposition. So additive manufacturing is all the rage. We think we know what it is, but it's actually changing every day. That was oversold about 10 years ago, but now the reality's caught up with the hype. We can make some amazing parts. Powder bed fusion is pretty well figured out. You can make real parts on there. We know where the business cases are. It still continues to grow. Binder jet, continuous fiber. Hybrid machine is where you grow the part additively and then you also machine it in the same operation. So you can machine faces that maybe are inside the part that are not accessible to a cutting tool using that method. And I'd also encourage you to come out for a tour and see our huge flex cell. We can fit roughly a 6 by 6 by 6 foot cube and print a part that big. So that's huge. So Advanced Technology Center, come visit us. We've got 3 sites. One is here. It's on campus with Pratt & Whitney and Raytheon Technologies Research Center. And we also have a site on Pitkin Street that's more of an industrial incubator space, although we do some training over there as well. And we have that composite center over at Goodwin University. So today we've got Alex Mitchell. He's a development engineer, very knowledgeable about this stuff. It's NC is the big name, and they have a couple different softwares they've developed. Adaptive machining software for the modern factory. So let's see if I can get this in a nutshell. Say you have a part, right? And now you have a weld on it, and you want to machine that weld and blend it. That used to be kind of hard. So you take your profiler part and you put a tool offset and you just keep ghost cutting, and you stand there and you crank the feed rate up when you're air cutting, and then you crank it back down right before you hit metal, and you try to blend that in. But I have to tell you, it never exactly blended in. So it's kind of hit and miss, because maybe the part's a little this way, a little that way, or the part's in tolerance, but it's not nominal. So you end up scarring the surface a little bit, or maybe you create a little piece of the program to do this, and then you have to try to blend that. And most of that was done offline. Some of it was online, and it's a highly manual, highly iterative, lots of steps task. So what Alex has got here today is pretty exciting, because it makes a lot of that very easy to do. And it does that through software. So I'll turn it over to you, Alex.
All right, thank you. Let me see if I can share my screen here. Can you see my screen? Yeah.
Yes, I do. You're not in presentation mode, but I do see your screen.
Yeah, let's flip this.
Perfect.
Good to go? Perfect.
Excellent.
All right. So I'm going to give a quick overview here. I want to thank you again, David, for letting us do this webinar with you. We're really excited about it. My name is Alex Mitchell, as you said. I'm the lead development implementation engineer at NC Software Solutions, and I work mostly with our adaptive software, which we call NC Transformer, or NCT for short. In this webinar today, we'll go through a few things. First, we'll talk about who we are as a company, then a little bit about what we make, what actually is adaptive machining, which you brushed on quickly there, and then what our software does. And then at the end, I have a simulated demonstration to kind of show you how our software looks and works in the real life situation. And then, as you said, we'll finish up with some questions. So NC Software Solutions was founded back in 2003, and it was built out of a need from several Boeing engineers. They were very intelligent guys. They still work with us. They're kind of our senseis now, but they've kind of taken a backseat role. And they needed software to help meet the tight tolerance requirements of the next generation fighter jets that were coming out at the time. So your F-22 was the main one. And they developed NCT to help meet those tight tolerances way back in 2003. And since then, we've continued to grow it and develop the product, and it's a pretty incredible product now. So NC Transformer will be our primary product I talk about today, our adaptive software, but we also have a couple other softwares. We have a machine monitoring software called MCS. We have a tool tracking software, which we call TAC, which tracks your tool throughout your entire factory. And if you want any more information on any of those, please don't hesitate to reach out to us. All right, so what actually is adaptive machining? So this is a question I get a lot. So in a nutshell, adaptive machining is technology that adapts manufacturing data to changing conditions. So in the past, as you described in your example at the beginning there, we used work offsets and cutter compensations, either diameter or length offsets, to adjust to what we're actually seeing when we cut the part. A lot of times you're cutting the part, measuring, cutting the part, measuring. This is a very limited process, and you're going to use a lot of rework. You're going to not always get the best part quality. With our modern adaptive application here, we're going to show you a process that can be ran on the front end of your process. It can be ran in real time, and update your process live to the actual conditions that you're seeing on your machines. So quickly, why do I actually need adaptive machining? Well, there's a lot of reasons why you need adaptive machining. And some people actually really can't do any of their parts without adaptive machining. But sometimes it just helps you a lot. So some examples is in your fixturing. With adaptive machining, you're not trying to make a very complex fixture that's trying to perfectly locate on your datums. Instead, you're just trying to hold the part securely. And then you're going to let NCT do the work of adapting your cut program to match where your part actually sits in space. So you can reduce your fixturing costs by sometimes a very large amount. And you can reduce the complexity of your fixturing. So it's much easier to load your fixtures. And it saves a lot of time for your operator. They're not over there trying to, shim that part in or make it fit in that fixture perfectly, because we're going to find where that part actually sits and give you a very accurate cut path. So that rolls right into quality as well. When you're using NCT, we're going to find where that part actually is. Every fixture isn't that accurate. So with quality, you're going to reduce your scrap, you're going to reduce your rework, you're going to cut once, you're going to measure twice, cut once, as the old adage goes. And I've done a lot of fixture design in the past, and I've had it where I've designed these fixtures and I thought there's no way this part can be loaded upside down. And then lo and behold, I'm proved quickly wrong by an operator. And with an adaptive solution, you're actually going to probe that part and see where that is in space. And you're going to see if that part's at least close to the right position before you put a tool to it. So you can rest easy that you know that that tool isn't going to hit that part. It's not going to run into it. It's not going to crash that machine. So it's an extra layer of safety and kind of foolproofing your process as well. All right, so our main product here, NC Transformer Adaptive Process, is kind of made up of a bunch of operations. And we have a couple of primary applications that do most of your adaptive machining. So that's our global orients and local orients, as we call them. And I'll explain those a little more later. And then we also have several kind of secondary applications that you can actually build right into your process with your adaptive process and run it in one swoop. And we'll see this in the demonstration as well. But some of these include on-machine inspection, feature correction, and 5-axis cutter comp. And I'll get into a little bit of what those actually are first here. So on-machine inspection, we've built a very easy to use on-machine inspection package that lets you quickly build reports. And it's built around a CAD/CAM programmer's capabilities. So we're not asking you to learn how to write DMS code or anything like that. We keep it really simple. And we allow you to quickly create inspection routines on your machine so you can get that live feedback to your operator to see how that part's actually cutting in real time. We also have feature correction. So this is kind of more of our post-process application. So we're going to take in measurement data, say from a CMM, from on-machine inspection, or maybe even like machine calipers from an operator measuring the part manually. And we can take that data and we can plug it into our feature corrections manually by having the operator read a report and figure out what type of offset he wants. Or we can make it automated through a closed loop situation. So data is going to automatically be fed back from a CMM or some type of measurement system. And using statistical process control, we can figure out what the part should be looking like compared to what it's actually cutting like. And we can dial that part right into nominal as that part keeps running. And then we also have 5-axis cutter compensation. I'll briefly glance on this. It's like kind of a separate product, but it is built in and we can use it combined with our adaptive processes. And this was built out of a customer need that they were doing some very complex parts with some very complex geometry. And they wanted to use cutter comp to reduce their cutting tool costs. But the typical CNC machine doesn't allow for very complex cutting tool paths. So we were able to build this product, and this is a long time ago now, and we have several customers using it now. And this product is able to use cutter compensation on paths like Kellering cutter paths on 3D surfaces, 5-axis swarf paths, zigzag paths. There's really complex circuital paths where your cutter just seems to get stuck back in the corner and your machine yells at you that, oh, I'm done cutting this now. And you've got to manually move it out. Our software is much easier to use, much more robust, and it requires no special lead-ins or anything like that as well. All right, so now our primary applications of NCT. So our first primary application is the global orient. And how a global orient works is we're going to probe a part, we're going to figure out where it actually sits in space. So we're going to see where that part sits. And then we're going to adjust the cutting path to match where the part actually is relative to its datums, rather than where it should be nominally. So what this allows is a very simple fixture setup, as I said before, but we're going to use a full 6 degree of freedom adjustment and recalculate your cutting tool path based on that part's actual location. So in the example here, I have 2 blades. If the blue blade is what it was actually programmed to, or the gold blade was its actual part, if we ran this part as is, it would be scrap. But we can come in with a probe, figure out where that part actually is, and adjust our cutting tool path to cut that part correctly the first time without having to do any rework or possibly scrapping that blade. And I like to compare this a little bit to how your CMM works. So your CMM, it typically runs through the part and it figures out where the datums are on that part, and it reorientates its probing routine to where that part actually is in space. And then it, when it measures the part, it actually knows where it is, and it doesn't really matter how accurately that part is positioned in its fixture. We're taking that same capability and putting it on the front side of your machining. So we're going to figure out where that part actually is in space, and we're going to update its cutting tool path to match that actual location. And you know, we had a customer that was really getting their butts kicked running some complex parts, and they kept going back to their customer and saying, we need you to open these tolerances up. We can't hit these tight tolerances, and they're having to pay a concession fee on every part that they're sending them because they're out of tolerance. And finally, they found us, and we implemented NCT. And not only were they meeting their tolerances, but they were now meeting well inside their tolerances. And instead of going back to their customer asking for concessions, they were asking their customer to leave those tolerances the same, because now they had a competitive advantage. And they are now one of our biggest customers with many, many machines running our software on all types of different applications. So that was global orient. We also have our local orients, and these allow you to kind of dial in on certain features with tight tolerances, or that are kind of separate from the rest of the datum scheme of the part. These kind of come in 2 different flavors. We have our simpler local orients, which are like planes, lines, circles. And an example here on the screen is, say we have a lug kind of like this, and we need to put in a hole pattern. We can probe the inside of this circle and set that hole pattern relative to that bore using a probe path. So it allows for really dialing in on certain areas. We also have our more complex adaptive local orients, as we call them. And these are more geometric based. So what I mean by that is we're actually going to match a shape to the part. So we're going to see what the part actually looks like shape-wise and match it. And in the example I have here, it actually comes from a real customer. We have a customer that was cutting these very large rings. And these rings weren't perfectly circular. They were kind of egg-shaped in reality, but the CAD CAM guy saw a circular ring on his screen when he was programming it. So real life did not match what he was programming to. What we were able to do is come in here and probe all the way around the inside of this ring, see what that ring actually looked like, and then adjust the cutter path to match that ring. This allowed them to, instead of doing this manually or trying to bend the part into a circular shape, quickly probe it, run it, and they're off and going, saving a lot of cycle time. These adaptive local orients have quite a few other applications and types. So some other types are meshes, splines, as I said before, cross sections, rolled surfaces, and I'll get into a little bit of these later. But some applications, and one you see on your screen here is for the surface of an airfoil. So a lot of times these airfoils need rework, or they need some type of casting gate machined off. But we can probe around those areas and see what that part actually looks like and adjust to them. And this is another customer example where we had a customer that was doing leading edge repair on airfoils. And what they do is they'd machine out that leading edge, weld in a new leading edge, and then they needed to push that off clean. But that airfoil had been running in a engine for thousands of cycles, and that looked nothing like what a nominal airfoil would look like. So what they were able to do with NCT is go in and probe it. And they took 8 hours of bench time. So a guy over there manually blending this part to less than half an hour using NCT by being able to probe and adjust the cutting path to match what that part actually looked like in space. Some other examples, like you said earlier, is the weld blending. I'm going to show you a little bit in demo. And another example is doing long beams for the aerospace industry. You know, you have these massive gantries, and they're 25 feet long. You need to probe all the way along the part, figure out where that part is. We can easily do that and adapt your cutting path to what that part actually looks like. Even though it's sitting there looking like a noodle when it's supposed to be straight, we can figure out what that part looks like and adapt to it. All right, so what does NCT implementation look like? That's probably a big question. I'm showing you a lot of really crazy stuff, right? A lot of adaptive. And it probably sounds like it's gonna be really complicated, but it's not. From an operator point of view, it's very simple, and you'll see that. But we want to plug right into your current process. We don't want you to have to learn a new CAD/CAM program. We don't want you to have to buy a new machine or a new probe. So we can use your current CAD/CAM program you're already used to. We're going to actually take the G code as it sits. We probably don't even need you to repost it or make any changes. And we're going to adapt that G code directly. We can use the same machine you're currently using. We connect to a huge variety of machines. There hasn't been many machines we haven't been able to connect to. And we can use pretty much any probe, Renishaw, Marpaz, anything you think of, we've probably done it. It's very quick and easy to set up, usually just a couple days, and we're in and out of your factory, and that includes training. For an operator point of view, it's like 10 to 15 minutes, because as you'll see, it's pretty much just clicking a button, hitting start. For your engineers, it's a little more complex, but not very much. And it's usually just a couple hours explaining how the stuff works. And we'll kind of work you through your first process. And after that, you're kind of off and running. A lot of times it's just a little bit of phone support here and there, and you're good to go. So I'm going to get into the demonstration, but first I'm going to kind of talk about what you're going to see a little bit in that demonstration. So this is the part we're going to see. It's kind of a long tube with a flange on top. The part I have is actually going to be deformed from what you see here a little bit, and we're going to move it off in space from where it was nominally programmed, so you can see NCT adjusting the program. First, we're going to start with a global orient to figure out where that part actually is in space. So we're going to do some points on the inside of the tube, a few points on top of the flange, and a clocking point, which will give us a full 6 degree of freedom representation of the actual part's location. This is an iterative alignment, so it will run a couple of times until it finds and makes sure it has the correct position of the part. And then once it has that correct position, it's going to check for any max conditions. So it's going to see, hey, is that part at least close to where it should be, or did this operator maybe load it upside down like we talked about before, or drastically put that part in the wrong position? And in that case, it can throw a warning to the operator to say, hey, you need to check your setup before anything happens that could cause a crash or damage to your part. After the global orient, we'll move on and we'll have an adaptive rolled surface along with a couple other local orients, which I'll get through here. And in this case, we're going to probe 2 splines along the sides of a weld. And then we'll use those splines to create a ruled surface and blend across this weld. And this comes straight from a customer requirement, actually, where we had a customer that was blending tubes together, or welding tubes like this together, and they're leaving a lot of gouge in excess that required a lot of bench time. We were able to go in and probe and make it so it blended off smooth, leaving no gouge or excess, and saved a lot of cycle time on their end, a lot of manual labor. Next, you'll see a kind of a simpler local orient, and that's just putting a slot down the center of this extrusion. We're going to probe both sides, create 2 lines, and then do a parallel lines fit up to make sure that that slot gets put straight in the middle of that extrusion. And you know, this is one that you might think, well, that's kind of simple. I could probably do the math for that and figure out on my own. But what this allows you to do is it's quick and easy. You don't have to check your math. You don't have to understand how it works. We're going to let you do it really quickly and easy. Just give us some points, say you're making a line with these points, and you're off and running. And then when your next engineer picks it up, he's going to understand how this works because you have a standardized process in place using NCT. All right, a couple more here. So next in the demonstration, we have kind of this welded on lug. And this comes from a customer as well, where they were machining a lot of holes, and these holes need to be put in perpendicular to a surface that wasn't at the same angle as they nominally programmed it. So what we can do with NCT is we can actually probe the top of the surface, create a plane from those probe points, and figure out where that plane sits relative to where it nominally should sit. And then we can also probe the inside of that bore and create a circle and use these two local orients together to position that hole pattern so that they're both perpendicular to the surface and relative to the center of that bore simultaneously. Then we'll have another welded on lug here. And in this case, we have a pocket that needs to be clocked relative to a hole pattern. So we're going to probe that hole pattern, a couple of holes, create a couple of circles, and automatically adjust that pocket to match that hole pattern. And then here we have an adaptive spline. So this is what I talked a bit about before. In this case, you can kind of see the red part overlaid with the blue part, which you'll see in the demonstration, where I've actually adjusted the part from nominal to look wildly different than the actual part looked like when it was programmed, up to 3/4 of an inch actually. So we're going to probe all the way along this spline, all the way along this edge, and then adjust this chamfer to follow that edge, even though it looks nothing like what it was originally programmed to look like. And then last here, we have an adaptive cross-section. So I talked a little bit about this with long beams on gantries, but even in smaller situations, like you'll see here, we can take a bunch of cross-sections along, in this case, a flange, and then we're going to use that to set a bunch of depths and locations of countersinks. So we have all these countersink holes. They need to be held relative to the edge and a depth relative to the top. I've drastically adjusted the part to look nothing like what it was programmed to look like. And we're going to see how NCT can adjust these countersink locations to actual conditions that you'll see on your part. All right, so I'm going to jump into my demo here. And Dave, I'm going to ask, can you see this all right? Can you see my Vericut and my NCT here?
Yeah, it looks great. I just want to drive home a point that you made, which is that this is largely online programming, right? So you already have your G code, you already have your path. You're just, you don't spend the time lining the part up. You don't have shims all over the place. That's really, it just continues to impress me. Yeah, it does look good.
Absolutely. Yep. We're adapting to your real life situations, not what your CAD CAM programmer sees when he's looking at his computer screen back in the shop.
Very cool.
Yeah. So what I have here is our operator interface, as we call it. We have an engineering interface where you actually set up your processes, but this is the operator interface, and this is what the operator will see down at his machine. And all he's going to see is a list of different parts that he can run that are set up by the engineer for that machine. I also have a simulation here, so we're going to use the simulation software to kind of show you what it would look like. We're actually using the same machine interface that we use between a machine, but we're using it with the simulator to automatically pull and push data. So you'll see how on the NCT side, he hits cycle start and can pretty much walk away. Real quickly though, I do want to show you the part overlaid. So you can see this part is drastically different than what is programmed. So the blue part is the nominal part that the programmer was programmed to. And then the red part is the part that's been adjusted to a real life scenario where it's been adjusted drastically from nominal. I'm going to hide it so that the simulation runs correctly. And I'm also going to adjust the location of this part off in space. So I'm going to throw some numbers in here that offsets where this part actually is so that you can see how NCT is going to actually find where this location of this part is and adjust to it automatically. So put some numbers in and 0.2, yeah, it works. So I've both twisted the part in all 3 dimensions and I've offset translationally in all 3 dimensions. So that part is nowhere near where it was actually programmed to. If I were to just run it, it would quickly scrap and crash into the part. So I'm going to go ahead and make this as big as I can here. And I'm going to hit start on the simulator. So this is the same as the operator. He's going to hit cycle start on his machine. And then he's going to come over to NCT, and NCT is going to tell the machine what part to run. So in this case, we're running this flange tube. A few things I want to point out here. We can automatically link setup and tool sheets automatically through your network, so you can bring these up live, so you can have live documentation through our thing. That's all this stuff's optional. It's kind of what you want to pick for your process. We also have what we call feature corrections. So in here, I have a bunch of different features set up, and I can manually move these features wherever I want, as I talked about previously. So in this case, we have this pocket here. and it's going to load from a database. So it's going to keep track of everything that ever happened. So every move that's ever been made, it's going to know what time it happened. And I want to get a little picture of what my feature looks like and how I can move it. So in this case, I want to move this pocket. Let's say we want to add a little bit of stock to the base. Currently, there's already 10 thousandths of stock being added, but let's add a little bit more. Let's add 5 thousandths more. And I can accept that, and I can hit return. So now I've manually adjusted, but I'm also going to automatically adjust using my probe in a real-time scenario. So the Vericut simulation is ready. I'm going to hit start on NCT, and it's going to connect up. And then it's going to ask for a serial number. This is also optional. We can track all your data back to a serial number if you like. So I can put in a number here. I can push go. And from this point, this is when the operator can just walk away. Everything else is going to be done automatically and run lights out. In this case, as we talked about before, it's going to do a global orient. I'll readjust this a little bit. So it's going to probe some points, figure out where the part is. Now, I'm not going to talk a whole lot through this. I'll let you kind of take it in as it's running here. All right, so it finished probing that first global orient. So it did that first iteration. It thinks it knows where it is, but now it's going to probe it again to make sure it's right. Probing that part again. And once it has these points, it's going to check to make sure, all right, how far off was it? And then it's going to check eventual tolerances that the engineer would set up for how far he can actually move this part without throwing an alarm. So we cleared the alarms, and then we're moving on to the local orients. So as I said in the PowerPoint before, it's going to probe along this weld here. And then I do want to make clear, we do have a 3D model inside of NCT, but it's just for showing what's happening on the machine. It doesn't actually use the 3D model. We're just using the G code to adjust your cut paths. So after the weld, it's going to probe some points on that extrusion we talked about. And then it's going to probe some points inside that bore and then a plane on top of the bore. And then there's clocking circles to clock that pocket. And NCT, you can see, is automatically pulling back all this data to live feedback, seeing what your part actually looks like. Doing a lot of checks in the background. If any of these points are outside of a certain tolerances, all these tolerances you can set up to make sure that your process ran accurately. Now we're probing along that edge to set the chamfer. And we're going to probe some cross sections here to set those countersinks so they follow that edge and depth-wise. I believe at that point, it'll move on to the NC program. So like I said, everything's happening automatically. NCT is pulling back these points. It's going to transform this program. The operator has no more intervention once he hits start and puts in his serial number. He's going to walk away. All right, so it's pulled all the points back. It's transforming the program. I'm doing a lot of local orient, so it takes a few more seconds than normal. With very simple programs, I mean, it's lightning fast, not even a second. But in this case, it might take 5 or 10 seconds to do all these transformations we talked about. I think this webinar is pulling down my CPU as well. There we go. All right, applying our feature corrections. It's going to upload NC program to the machine. And start cutting that part. So all this happens automatically. There's no need to look at all the math. If anything goes wrong or if any tolerances are exceeded, all that's going to throw a warning to the operator and show them that, hey, something's up. It's a very closed loop, lights out situation. I'm going to speed it up just a little bit so we're not watching this thing go forever. So cutting those countersinks. At the end there, I'll kind of zoom in. I'll show you how it looks after it's been adapted. Cut this pocket. This is the pocket we've added a little bit of stock to in our feature corrections. It's going to run a quick inspection at the end of this and actually show us that stock on there. A quick demo of our on-machine inspection as well. And then we're going to blend out that weld. Oh, nope, I lied. We're going to cut the slot here first. Well, speed it up just a little bit. This weld takes a minute. So I'll show you later that this weld's actually been adjusted so that there's actually a mismatch between the two sides. We're not going to leave any gouge or excess as it would if we'd ran it nominally because we probed up both sides of that weld. Speed up just a little more. And I think the last thing here is our chamfer. And then we're going to run a quick inspection routine on machine inspection. And then I'll explain a little more.
I appreciate that in your demo. You made it just so visually obvious how far it's running out. Like probably we wouldn't have a part that far out, but when you're cutting a chamfer, if your part's even out 5 thousandths, it's just so visible. When you're out around by 5 thousandths.
Yeah, see that chamfer getting smaller and bigger as it goes along.
Yeah.
Yeah. It's a quick inspection here. Going to probe some points inside this pocket, and then it'll be wrapped up. And I'll go through a couple things real quick. All right, so let simulation stop here. Parts finished. We've pulled back these numbers, so if I bring up those numbers again that I originally put in at the very beginning of the simulation, so when I move the part, we can see that NCT's found the location of this part within about 1/10 in translation and about 5/10 in rotation angles. So we know exactly where that part is, and we've adapted that cut program to match that part's real location. I can also re-enable the nominal part, and we can kind of see here, this top, just like you're talking about, this edge here, I've actually added almost 3/4 of an inch in areas where we've adapted that countersink, that chamfer, to follow that edge. And this is way larger than, like you said, it would be normally, but it shows you just how powerful NCT is and how nice of an edge you can put in, even when you have some drastic moves. And the same thing with holding along this edge with the countersinks. If I zoom in here, you can see there's actually about a 70 thousandths mismatch between these two edges and where it was welded together. And we were able to blend that out perfectly. One thing I think is really cool is just how far off this is. I mean, we were able to adjust that cutter path to match the location, both perpendicularity and location of that bore very easily, just with a couple of probe points. I am going to jump back over to NCT here. I can quickly show you here. I'll load this up. This is the inspection report. It's just a PDF report. We do allow for XML and CSV as well, but we can see that 15 thousandths deviation that we've added to the floor. So we had 10 originally, we added 5 more to it. So now instead of being 1 inch deep, it's only 985 deep. This report's very easy to make. You can make it on the fly. Most of the data is automatically pulled from your process that you had already set up. And I just want to point out that how easy NCT is to use for the operator, but also for the engineer. The operator's done at this point. He's going to hit home, click on his next part he wants to run, and he's off and running. And at this point, I think I'm done with my demonstration. If we want to open up to any questions, David, or anything you want to say.
Yeah, what a great demonstration. It's really cool that you had Vericut there to show the machining part too. It's always exciting to see a real machine tool and coolant come on and off, but it really drives the point home well. So thanks for that. So
No
I'll
problem.
give a couple seconds for attendees. We do have a handout I'll point out as well. It's nice of you to provide the slides in the handout section. So if you want a copy of that, just grab it from there. If you want the CCAT slides, you can reach back out to me as well. So yeah, feel free. Throw the questions in the chat. If you click on the caret, like the rightward facing triangle, you can drop questions in there. But I have a couple questions here for you. Does your software only work with certain probes, CAM software, or machine controls? So kind of where are the limits on that?
Yeah, so we support all major machine controls: Akuma, Fanuc, Haas, Siemens. We also support all major probes. So Renishaw, Marpaz, Bloom, we've done a lot of them. And then on your CAD CAM side, as I said before, we're actually going to just use your G code. So you can continue whatever CAD CAM system you're currently using, whether it's eSpirit or NX or CATIA, whatever you guys are comfortable with, you can stick with what you're good at.
That's great. So a question building off that one. So you've got a part and you've already got your G code, you've got your program. Now you have a change, or maybe it's not a repair or a weld like you showed, but maybe you've got a forging, right? Those forgings, those castings, sometimes they come a little wonky and we
Yep.
spend time chasing them around. So once you post out your code, just quick walk us through it again. We're not looking at posting a new G code, right? We're modifying the code. Is that correct?
Exactly. So we're going line by line, figuring out where your X, Y, Z positions and your rotary positions are, and we're updating that code. So if you need to change, feed or speed, and you need to repost your code, on our point of view, you don't need to do anything special. You just repost, and it automatically will pull in that new code the next time the process runs. So it's very easy to make changes in the future. And from our side of view, it's automatically going to make those adjustments without any need for an engineer or an operator intervention.
That's great. And that's also distinctive. We were talking about this a little bit before we brought the webinar on, but so many times there's kind of a locked process, right? Where it's locked down. You can't post it out in G code. It's approved. But because this uses adjustments, it's a different thing than posting out a new G code, right? You're using the same G code and you're processing it. So just be absolutely clear. That's what we're doing. Very cool.
Yeah, exactly. So no need to buy, expensive CAM product on top of our product.
So is your product a subscription, or you buy it and then you own it?
You buy it and then you own it. We do apply a maintenance fee, but that includes your support and updates. And we try to keep a very close relationship with our customers, and they come up with all kinds of needs over the future, and we help them through that as part of that maintenance fee.
That's great. It's kind of like buying expertise, because when I was a tool maker, this was something that the most experienced tool makers would do, and they didn't really like to show anybody how they did it, which I get. It took them a very long time to learn it, and that was kind of their proprietary thing. But here we've got a tremendously powerful tool that you could have a good tool maker do it, or maybe a mediocre one, or maybe one that's just starting out that doesn't really even understand or appreciate how hard this stuff is, because they've got a 5-axis machine and the tools. So that's pretty cool.
Exactly.
So how long does it usually take to set this up? Say, hey, I want to have this, how much downtime am I looking at on my machine, and so forth?
So we've actually done some really cool stuff with customers that were a little tentative about picking up this process, where we've actually had them send us, have them run a probe program. We don't even come on site yet at this point. Have them run a probe program. They send us the data. We actually transform their program remotely and have them run it without us even coming on site to prove our process works. Once they're ready to go and can accept that our process does work, we can come in, we can install and have it up and running in about a day or two. And then after that, it's a little bit of training to explain it to operators how to use it. And then within 2 or 3 days, we're back out the door and you're up and running the highest quality part you've ever ran.
That's great. And I didn't check this question with you ahead of time, forgive me, but it occurred to me, does this work with grinders as well? Or is it just milling machines? What kind of applications have you seen this work on?
Yeah, so any type of um, G code we are applicable to. We haven't done grinders, but it would have no issue with that. We have done water jets and EDM machines before. So there's quite a few different ways that we've adjusted the G code to match real life scenarios. Great question.
Very cool. So how long does it take an operator to learn how to use this?
Yeah, like I said, and what you just saw, I mean, it's pretty much for the operator just selecting which process he wants to run and hitting start. So from an operator point of view, it's very simple. And we do have another application for if you have a robotic cell, we do have an automated solution as well to work with robotic cells as well.
Neat. Well, we'll have to take you up on that because we've got quite a few robots here at CCAT.
Robots are a
So
lot of
if you
fun.
think of more questions, reach out to Alex, reach out to me. This isn't really the end. This is kind of the beginning of when I tell you guys about how to get hundreds of thousands of dollars from CCAT. So CCAT is a not-for-profit. We administer grants on behalf of the state of Connecticut. I think we also work on some federal grants. I'm not sure which ones are most active right now. But if we could have the next slide, please, I'll tell you guys a little bit more about that. So with all this advanced capability in industrial Internet of Things, you really need to have control on who sees how much in your company and how stable you are. The worst thing would be to have all these advanced 5-axis machines with the latest sensors and then have somebody just kind of wrap it into the device with them or something like that. It's pretty far from happening, but you'd be surprised what people have for the default passwords, how out of date their firmware is. And there's some money available with that, a SIRI Cyber Assistance Program, Smart Industry Readiness Index, SIRI, different SIRI than I'm saying that, my phone's going off, I have to shut it off. So it's $10,000, that should go pretty far. We've also got an Internet of Things integration voucher program. So that's a one-to-one match. So this is $20,000. So if you spend $40,000, the grant would match you one-to-one. So it'd be 20,000 of the grant, 20,000 is you. So it's for Internet of Things solutions, and this would seem to be an example of that. So I would encourage you to apply for that grant. We also have a manufacturing innovation fund program. So if you're thinking, boy, a cool solution ever, but I'm on 3-axis, I think you could still find use for the software on 3-axis as well.
Yep.
But if you're at 2.5, maybe it's not quite as useful. So if you need more axes in your machines, more equipment, so forth, drive productivity, you need probes, you need a lot of this stuff, and you've already spent out the IoT, IVP. We've got the MVP. So this is a 2-to-1 match. So to get all $100,000, you spend $300,000, which is pretty easy to do when you're buying robots and machinery, but it's also pretty easy to make your money back when you've got really good solutions. And you don't have to spend all 100,000. It's not one and done. I forget what the threshold is. You can't apply for it for 10 bucks, nor would you. But the application process is pretty streamlined. It's right on CCAT's website, and those grants are getting approved every day until the money's spent. So do reach out. So apprenticeship funding, it's a wage subsidy for registered manufacturing apprentices. So you hire somebody on, they get through their trial period where they're on kind of probation, fire them, and they never can collect or whatever for the first 30, 60 days, what have you. And now you're going to teach them a trade, or maybe they have a trade you'd like to be able to train them more. CCAT administers this funding from the state of Connecticut. It's $15,000 wage subsidy. You just register them as an apprentice toolmaker, apprentice machinist, what have you. And then this picks up a lot of the cost. So now you're looking at free software, you're paying a wage subsidy while they learn how to use it, and now you've got a toolmaker that has these incredibly advanced capabilities, and the money's here for you. So incumbent worker training, $50,000 to assist with upskilling, training your employees. So you got somebody that's been around for a while and they're ready to change roles, what have you. You'd like to bring in new technology. So we've got some training for that too. There's more details on all these programs on our website. And engineering internship program, cohort-based program for interns at companies with 2 200 employees or less. So I guess there's some money there too. That one's new to me. I don't know a lot about it. And now the next slide, very dear to my heart, introductory workshops. This is an example of one. We tried to bring it to you during lunchtime, so hopefully it's easy and convenient. Thank you, Alex, for working through lunch with me to get this info out to people because it's really incredible. A demonstration project. Today, Alex was able to completely demonstrate the project from start to end. That's not always the case. Sometimes I need to come out to you, which I'm very happy to do. And I will do a demonstration project with you. Sometimes I do it myself. Sometimes I bring in a subject matter expert. But if you'd like, and you're in Connecticut, reach out to me and I'll schedule a time. I can come see a little bit about your organization. If you have something specific that requires an NDA, we can get that done. But usually the demonstrations don't even require one. I can just show you something like this where I don't even really have to see your part. Just see a little bit about what you do, and I can tell from 50 feet away that this is an applicable solution that you need to know about. And other things I really need to work one-on-one with you on. So I can do that. We've got the money for the grants. We've got technology onboarding support, and we've got continued training. So definitely keep up on our site. If we could have the next slide, please. Thank you, Kira. So Industry 4.0 training. We've done so many trainings that with the demonstration projects, you'd be amazed how busy we are, or maybe you wouldn't be. So this is no cost. It's 180 skills. It is somewhat general, but it's surprisingly high quality training, at least the robotics one I can speak to. So if you're looking at or even considering robotics, you can get set up on bit.ly/180 skills. So we made the link real easy for you. You can write that down, and if you want, email me and I'll send it to you. But you have to take at least one Industry 4.0 technology class. So I've done the robotics ones. I've not done the other ones. I probably should. Well, I have access, but I get involved with so many cool projects. If we could have the next one, please, Kara. So Advanced Technology Center tours. We're having a tour September 29th from 4 to 5 and November 29th from 2 to 3. So if you're a US citizen, US person, you can come show us your license with the gold star on it. Otherwise, bring your passport, birth certificate, what have you, because we're an ITAR facility. And come on in, check out our robots, look at our software. I'm going to be working with Alex to get a copy of his software here at CCAT so you can try it hands-on. If you want a real expert to run it, I'll email Alex. And we'll show you what it can really do. We're also hosting NX University Siemens training. So make sure you reach out, register for that. It's a whole day training and you'll learn a lot more about advanced capabilities in NX. Collaborative robots coming up very soon with my colleague Sam. That's hybrid. So you can come down to CCAT if you want hands-on, or you can participate virtually like we're doing today. We've got a 3D printing forum and a smart manufacturing summit as well. So I guess that's it. We've got a thank you slide. Again, my name is David Morganson. I'm a manufacturing applications engineer in our advanced design automation metrology department. And thanks for joining us at our webinar. Take care. Thank you, Alex.
Have a good day.